Today I will train my army.
Oh, how many soldiers?
100.
Only 100?
Yes, a small but powerful army. Every soldier here could crush a battalion.
Okay, Commander. What is your strategy?
Simple. Moving in 4 directions. All units advance on my mark. North, south, east, west, simultaneously. No hesitation.
That's it? The most advanced military strategy ever created.
Increase my army.
How many?
Make it bigger. I want 2,000 soldiers.
Are you sure, sir? More soldiers mean more calculations too.
Nonsense. A great commander needs a great army.
Okay, let me see your code first. A typical MonoBehaviour.
Excuse me? I am not a typical anything. I am the commander of this army. Question my rank again and you'll scrub latrines with your tongue.
I mean your code, not you.
My code represents me.
That's exactly why I'm worried. Fine. I added 1,500 soldiers.
Excellent. Soldiers, move. Why are they so slow? Move like your life depends on it, because it does.
Let's ask one.
Soldier, why are you moving so slowly?
Sorry, Commander. I am waiting for Steve,
Who the fuck is Steve?
the soldier before me.
Why are you waiting for him? We march on schedule.
Computer updated Steve first, then me, then next.
How many soldiers are there?
Sir, about 1,500.
So you're telling me my entire army is waiting for fucking Steve? Who even are these cowards delaying the battle?
Basically, because right now your code works like this. Soldier 1 moves, then Soldier 2, then Soldier 3, and then Soldier 1,500 moves. Everything happens one after another.
Why doesn't everyone move together?
Because your calculations are running on one CPU core.
And the other CPU cores?
They are basically sitting there drinking coffee and they are actually unused. Let's open the profiler. As you see, the loop for soldier movement takes around 5% and 6 milliseconds.
Then what do we do? Buy a stronger CPU?
No, we use the power you already have. We do this by Unity job system.
Jobs! My soldiers need jobs now! They're trained to kill, not file taxes!
Not employment, a programming system. The job system allows us to split the work between CPU cores. Instead of all soldiers beyond core 1, we do this. For example, core 1, it handles 400 soldiers, core 2, another 400, and it depends on how many cores you have. So it is multi-threading.
So everyone finally moves together!
Exactly. Now let's replace our normal loop with a job and see what happens. Here is how to do that. First, make sure you install these packages, Burst Collection and Mathematics. Then we add a new C# code called Move Army Job. First, we include all the namespace we need. Unity.jobs gives us access to the job system. Unity.burst lets us compile our code into highly optimized native machine code. Unity.collections contain native collections that are safe to use inside jobs. Unity.mathematics provides higher performance math type used by the burst. And UnityEngine.jobs gives access to transform access array, which allows a job to safely update lots of GameObject transform. We use burst compile. Without burst, the job would still run on multiple CPU cores, but with burst, the calculations become much faster. We are implementing IJobParallelForTransform. This tells Unity that we want to process many transforms in parallel. Instead of one CPU core moving every soldier, Unity can distribute work across multiple CPU cores. This is for how far the knight moved this frame. Every soldier will receive exactly the same movement. I also mark it as read-only because the job only reads this value and never modifies it. That helps Unity optimize the job safely. This is the direction every soldier should face. Instead of calculating the rotation for every single soldier, I calculate it once outside the job and simply pass it. This is just a flag telling the job whether the knight moved this frame or not. If the knight didn't move, there is no reason to update thousands of soldiers. This is a function Unity automatically calls for every soldier. The index tells us which soldier we are currently processing. If the knight didn't move, we simply skip the rest of the work. No reason to waste CPU time. Move this soldier by exactly the same distance that the knight moved. Finally, rotate the soldiers so they are facing the same direction as the knight. Okay, the soldier script and the knight script stays exactly the same. The only thing we need to change is the army manager. Normally, jobs cannot directly access GameObjectTransform. Transform Access Array is Unity's special container that allows a job to safely work with hundreds or even thousands of transforms in parallel. First, I create a normal array that will hold every soldier's transform. Then I loop through every soldier and store its transform inside this array. Finally, I convert the normal transform array into transform access array. This is the object that will be passed into the job. I start with a default rotation. If the knight moved, I'll calculate the direction everyone should face. Notice I calculate this once instead of calculate it for every soldier. Now I create an instance of my job and pass all the information it needs. Think of this like filling out a form before handing it to the Unity's worker threads. This is where the magic happens. Instead of moving every soldier myself, I schedule the job. Unity now distributes that work across multiple CPU cores. This tells Unity to wait until all worker threads have finished before continuing. That way, I know every soldier has finished moving before the next frame begins. The job can move and rotate soldiers, but it cannot access the animator component, so I still update the walking animation on the main thread. This frees the memory and prevents memory leak. Now, let's run the game again. Our soldiers still behave exactly the same, but if we open the profiler, the CPU time for army movement has dropped from around 5% and roughly 6 milliseconds to around 2% and under 3 milliseconds. That's a significant improvement. All we changed was how the work was executed. Keep in mind that this is a very simple example. The real strength of the job system becomes much more noticeable when you're performing heavier calculations like AI, pathfinding, procedural generation, or other larger batch of math. And if I want to push performance even further, the next step is using Unity ECS, where your game is built around data-oriented design instead of traditional game objects. I've already covered that in another video, so make sure to check that out. Thanks for watching.